So good afternoon students. Again I come to the course of your math 1, that is BSM 101. So I have left my class at that point of continuity. Now I will start again from your differentiability. So today we will see that how we will test a function whether it is your differentiable at a particular point or not, that thing, and then after some of the results that will give us the very preliminary results. We may have done that one. So let's say start with that of how to test the differentiability. So if I am going to the differentiability, as you know, if you have a function, so if you have a function f of x and you want to test that the function is your differentiable or not at a particular point, suppose x equals to 0, x equals to a, then we have to test one thing by geometry, that at each point of this function at the point x equals to a, whether we can draw the tangent at that particular point. But in case of your mathematical expression, we need to be compute by the first principle of derivative. We know that a limit as h tends to 0, f of a plus h minus f of a divided by h. If this thing will exist, if this limit exists, then we can say, and that gives you some finite value. Of course, the existence gives you the finite value, and then we can express that this value is equals to your f dash. We denote that one by the notation. Sometimes it is also denoted by your df by dx at the point x equals to a. We have already seen that limit is our fundamental operation, and from there we have seen that how to test a limit exists or not. So by that criteria, if you have to verify the function has its derivative, we have to test that this limit is your exist or not, and for that existence we have to consider the two cases. One is called your left hand derivative, another is your right hand derivative. So in that case, if you are considering that as h tends to 0, your left hand case we consider that as h your tends to 0 minus, and for right hand you have to consider that as h tends to 0 plus. And accordingly, for both the sides, your limit as h tends to 0 minus and h tends to 0 plus, if you are getting the value is your finite equal, and then we can say that the value of this limit is equals to your f dash a, and if such thing will happen, then we can say it is your the derivative of the function at the point a is your exist, and that is denoted by this one. So if I go for your some function, say geometrical representation of that any function, or whether the differentiation of that function is your exist or not. So if you have a graph like this, then you can see between the interval a and b, if you consider any point c here, c, then we at this point we can draw the tangent of this graph. We can draw the tangent to this graph at this point. So we can claim that this tangent makes an angle with the positive direction of your x-axis, so that slope is denoted by the derivative of that function also. But if you have a function like this, then we cannot claim that the function has its your derivative, because if you are drawing the tangent at this point, in which direction we will draw, whether the tangent will comes in this direction or the tangent will comes in this direction or the tangent will come in this direction, we could not be confirm this one. So therefore we could not draw the tangent to this particular type of curve. So the derivative of that function at that particular point, suppose it to be your c, we could not find the derivative of this function at this point c. So these are the some features for which we can claim or we can verify that a function's derivative is your exist or not. Rather than also we use to verify that a function has its your exist derivative is your exist or not, that can also be computed with the help of your differentiation by the first principle of derivative that we get. Now different rules of your derivative I am not going to, because you have already gone through that those rules. That is, your derivative of x square is equal to your 2x, e to the power x is x, log x is your 1 by x. So all those rules is known to you. I am not going through that one. Rather than I skip that part also, it comes to the application of your derivative. So that is called the Rolle's theorem. Rolle's theorem says that if you have a function which is your single valued, that is most important, we will see why this is important. The function is your single valued over the closed interval AB, and thereafter the function is your continuous in the closed interval AB, function is your differentiable over the open interval AB. That means that extreme points we are not being considering here, and the functional values at the extreme points are your equal. Then we can claim that the function, you should have one of your point in between your AB for which the derivative comes to 0. And derivative comes to 0 means we can claim it to be that the function has its at some point the tangent to that function will be parallel to your x-axis. That's our claim. That's the claim, is it? So these are the conditions. We will see later on that these conditions are your sufficient, but they are not your necessary condition. So I'm not going to the proof. Proof is not required here. Rather I come to this geometrical interpretation. So if you consider the function f of x, this part is your f of x. This part is your f of x. So if you consider here the function over the interval AB, we can see that the function is your continuous because there is no break in the function. So we can claim it to be your continuous function. We can claim also that at each point to this function we can draw the derivative, we can find out the derivative because we can draw the tangent at each point. The tangents at each point exist, and tangent we can draw. So therefore the derivative at each point of this function is your exist. And then after the terminal values are your same by the drawing of this functional, that is fa equals to fb. So these these two length are your same. So therefore we can claim that this function satisfying the Rolle's criteria. So therefore there should have some point c in between ab at which your f dash c comes to your 0. So that we can claim that the tangent to this graph, there is one point at which your f dash c comes to 0. That is, the tangent is parallel to your x-axis. Similarly, instead of this one, if we draw the graph like this way, we can claim it to be that your f dash c equals to your 0, because the function, again you can see there is no break, so the function is your continuous. The function is also single value, that criteria is required. So the function is your single value, function is continuous, there is no break in the function. At each point we can draw the tangent to this function. Then we have some point at which the tangent to this graph is parallel to your x-axis. Now instead of your one point c, we can get more than one point. Here we can see the graph which has its your more than one point, that is c1 and c2. Over that interval the functional values are your same. The thing is, we have claimed every time the function should be your single value. If it is not being, then we can see that you have a graph, suppose you have a graph, suppose you have a graph in between your a and b. This is supposed to be your f of x, y equals to f of x, and over that interval the function is defined, the function is also continuous. At each point we can draw the derivative of that function, but the thing is the function has its two value. If you consider any functional value herein being the continuous, it has its two value. So such functions we could not be considered here for satisfying the Rolle's theorem, because you have 2 points which have its your tangent parallel to your x-axis, and both the points are your outside the interval. That line between the point which we can consider to be your c1, and that is the point your c2, they are lying outside that interval. So it will not be satisfy the Rolle's theorem, and therefore we are getting the points which are not being inside of that the interval AB exist. So that the single valued criteria is one of the most important criteria for that. Here we consider one example that if you consider the function f of x equals to x cube minus 4x over the interval your minus 2 to 2. So since the function, we can verify that this function is your single valued function. If you put any particular point in between minus 2 to 2, you will get it to be, that will give you one value for that function is. Now the function is also continuous because fx is a polynomial function. So since fx is a polynomial function and it is defined over a finite interval, that is minus 2 to 2. So it is continuous because polynomial functions are continuous everywhere. So fx is fx is continuous over the interval, of course, your minus 2 . So the function is your continuous. Now the next we have to verify the differentiability. So if we find out that f dash x by the usual rules of the derivative, we are getting that 3x square minus 4, and that is over the interval minus 2 to 2. We know that for any values of your minus 2 to 2, it will not be come infinite. That will give you every time to be a finite value. So we can claim that this derivative is your exist. And then after the terminal values, that is f of minus 2, we have minus 2 cube minus 4 into minus 2, which comes to be minus 8 and plus 8, and that is your 0. Whereas f of 2, it comes to 2 cube minus 4 into 2, so that comes to your 8 minus 8, that is equal to also 0. So we are getting that f of minus 2 equals to f of 2, f of minus 2 equals to f of 2. So it's satisfying all the criteria for your Rolle's theorem. So therefore by Rolle's theorem, so by we have, there is a point C for which your f dash C equals to 0. By Rolle's theorem, there exists C belongs to your open interval minus 2 to 2 such that f dash C equals to 0, and we can get the point C which will lie between your minus 2 and 2. You can find it out. This point will be your 3c square minus 4 is equal to 0. So therefore c square equals to 4 by 3, and this implies c equals to plus minus 2 by root 3. You know that the point is your 2 by root 3 will lies between your, so both the points comes to your lying between your open interval minus 2 and plus 2. So therefore we are getting, instead of your 1, we are getting 2 points. This one function. We have another function, that is fx equals to the fractional part of that of any number. So in this case we can say that f of x, if you consider that fx equals to the fractional part of your x, and that x lying between the open interval ab, open interval 0, closed interval 0 and 1, this function is your the derivative of this function in the open interval 0 and 1 is always every time it comes to be your 1, because we know that f of x equals to x for all x belongs to the open interval 0 and 1. There is no change, but because the number which are lying between your 0 and 1 is your fraction, and being of that fraction, then f of x comes to your 1. But the thing is, if we consider the function's continuity, in case of your fx, this is equals to comes to your 0 when x equals to 1, because it has no fractional part, so we can write it down that the functional value comes to be your 0 when x equals to 1. So therefore, if you are taking the left hand limit of this function, that is limit as x tends to your 1 minus f of x, we are getting that value comes to be your 1. But if you are taking the functional value at the point x equals to 1, which is not equal to your 0, which is your f of 0. So sorry, which is your f of 1. So we can claim that fx is not continuous. Fx is not continuous over the interval 0 and 1. And since it is not continuous, so it will not be it's not satisfying the Rolle's theorem. So we can claim that the function doesn't have any point in between which the tangent will be parallel to your x-axis. We have the next that is discussed for the fx equals to mod x. So consider that fx equals to your mod x, and for that mod x we have x when x is greater than 0, equals to your 0 for x equals to 0, and equals to your minus x when x is less than 0. So you can see that part wise it is a polynomial function and they are meeting at the point 0. So if we draw this represents a continuous function in between the interval, your any interval if you consider, that is in particular minus 1 to 1. So if you consider this one is your minus 1, this one is your plus 1. So in between the interval minus 1 to 1, we can have your the function is continuous. There is no break in the function. So we can say that the function is your single value. So fx is single valued continuous function over the interval your closed interval minus 1 and 1. But if you consider the derivative of that function at the point your 0, so we have that limit as h tends to 0, f of 0 plus h minus f of 0 divided by h. So if you consider the left hand derivative, that is h tends to 0 minus, that time you have limit as h tends to 0, this is f of h, and that f of h, since h tends to 0 minus means you know that h is less than 0, and because of h is less than 0, f of h, that f of h minus f of 0 divided by h. So h is now tends to 0 minus. So because of that 0 minus, h is less than 0, you have that f of x is your minus x. So that comes to your minus h. So this is equal to limit as h tends to 0 minus. This comes to minus h by h, which is equal to your minus 1. Whereas if you compute that the limit as h tends to 0 plus, f of h minus f of 0 divided by h, and for that h tends to 0 plus, this is your h is greater than 0, and because of h is greater than 0, that f of x gives you the value x, so that is h by h, and that ultimately gives you h by h, which is equals to your 1. So we can see that the derivative of this function at the point 0 does not exist. So since the derivative of this function at the point 0 does not exist, the function is you're not differentiable over the interval, open interval minus 1 and 1. So therefore Rolle's theorem will not satisfy. Claim that the Rolle's theorem will not satisfy. Next one is we consider the function. So this problem I will leave for you. You just see that this is also your polynomial function, and being a polynomial function, it will be continuous everywhere. We have not been defined for this function any interval. Over any interval you can verify. So this polynomial function is your continuous everywhere. If you want to find it out, the derivative will also be exist for any finite values of your interval. If we consider that the interval is your AB, we can consider here for over some particular interval, say AB. So over the interval AB, it will give you some finite value because it will not be any of the part will not become in the denominator. So therefore we must get some finite values are there. And if you compute the FA and FB, FA is also 0, FB is also 0. And then after we can find out the point C, which will be lying in between your A and B. So that we propose for you as a homework. Okay, so that's all. So we have seen that the Rolle's theorem and some of the problems we have solved by this. Now we will see that this Rolle's theorem is not your the necessary condition. This is actually only the sufficient condition. So by that example, if we consider one example, to know that this is your only the sufficient condition. We consider the function, suppose f of x, which is equal to 1 by x plus 1 by 1 minus x over the interval if you consider that is 0 and 1. Then it is very obvious the function is actually not defined at the point 0 and 1. So the test at these terminal points of its continuity is not being there is no question about to test that at these 2 points the function is your continuous or not, because the function is not defined particularly. But if we are going to find out the points, we can see that if dash c some point, then we are getting minus 1 by x square. This is minus 1 by 1 minus x its square, and for this minus it comes to plus. So if you consider this one to be your x and make it equals to 0, so therefore if we consider the point C, there exists C belongs to your open interval 0 and 1. If there exists C belongs to 0 and 1 for which f dash C equals to 0, then we can have minus 1 by C square plus 1 by 1 minus C its whole square equals to 0. And from here we can compute that 1 by 1 minus C its whole square equals to 1 by C square. If you reverse these two, we can have this C square equals to 1 minus 2C plus C square. And from here we are getting that C comes to be your 1 by 2. So we are getting a point half which is lying in between your open interval 0 and 1, though the function is not satisfying the criteria of your Rolle's theorem. So therefrom we can claim that these conditions are only the sufficient conditions, but they are not your necessary conditions. We have some consequence from the Rolle's theorem is that if you have a function which is continuous over the closed interval AB, and the function is also differentiable over the open interval AB, and we have 2 points at which the functional values comes to 0, or we can say that the function has its 2 root over the closed interval AB, then we can get one root in between your open interval AB of the derivative of the function that we can claim. So this is very as a usual consequence of your Rolle's theorem, because Rolle's theorem says you the function f of x is continuous, and we are considering here the case of over the open interval AB. We consider that f dash x exists over the open interval AB, and we know that in case of your Rolle's theorem we have that FA equals to FB, and we are considering instead of this a particular case, that is FA equals to FB equals to 0. If it, or it may be that instead of your AB, at some points x1 and x2 in lying in between your AB, then also f of x1 and f of x2 is 0. That is this one, or for some x1 and x2 belongs to, you can consider the open interval AB, such that f of x1 equals to f of x2 equals to 0. And by this rule, that if f of x1 and f of x2 equals to 0, so we can, instead of AB, we can consider the interval to be your x1 and x2. Instead of AB, we can consider that the interval is your x1 and x2, on which the Rolle's theorem will be satisfied. And since the Rolle's theorem is satisfied over the interval x1 and x2, so we can claim that one point should be there in between your x1 and x2, say C, for which your f dash C equals to 0. So there exists C belongs to open interval x1 x2 such that f dash C equals to 0. So since f dash C equals to 0, where C lies between open interval x1 x2, we can claim that this C also belongs to, that also gives you the belonging to the closed interval AB, or we can say that the open interval, of course the open interval AB. Open interval AB, because we have chosen that x1 x2 from your open interval AB. So therefore we can say that the function has its your one root. If a function has its your two roots, by satisfying the Rolle's two conditions of the Rolle's theorem, then we can have the function's derivative also have its your one root in between that interval. That's another consequence we can get. If we have the function in the particular case, that if you have the function is your continuous, so you can see that the case is for a continuous function. So continuous function means it is continuously, of course it is your single valued over the interval AB. The function is continuous in between this A and B, there is no break in the function. At each point the function's derivative is exist, and we know for the derivative of a constant function, if you consider that fx equals to your k, then f dash x is equal to your 0. So that f dash x equals to 0 gives us that each point the function has its your derivative, and therefore we can claim that the function's derivative exists over the open interval AB. And since the function is constant, so whatever be the point A and B, the functional values always remains the same. And then finally we can claim that there is a point C in which there exists C in AB such that f dash C equals to 0. Now you see that what that C is, that C is not only the one point. That's why the Rolle's theorem says you, instead of your one point, you can have more than one points. But in this case, the C is your many, infinitely many points, or we can say all the points which are lying in between AB, you can get that f dash C equals to 0. So instead of your instead of your countable number of points, you can have your all means infinitely or countably infinite number of points for which your f dash C comes to 0. And that is a particular case of your Rolle's theorem. That is when fx is your constant, then not only the n points we can consider, then all the points are also your extremum point. We know that to find out the extremality of a function at some point, we need to be compute that f dash x equals to 0. So that's all for your Rolle's theorem statement and its consequence with some examples that we have been verified. Next class we will do the Lagrange's mean value theorem. Our next topic is on Lagrange's mean value theorem. So that's all. Thank you for listening.